a doctor of optometry and a fellow in the College of Optometrists for Vision Development. So my unique take on all of this is that I'm a clinician, and so I see patients that have eyes like this. Most of the patients I see are developmentally delayed or they have brain injury. So some of the insights that I have are how we first as scientists learned about vision in the brain. And that's when there's a damage to a certain area and then a loss of function. So now we have some neat advanced technology where we don't have to have brain injury to discover how the vision works with the brain. As far as vision goes, most people think you're an eye doctor. You make me have some glasses to see 20/20. That's such a small part of what we do with vision. When I talk about vision, I want to make sure that you can see clearly and seamlessly, and your eyes are nice and steady, and we acquire that information normally. The second part of that is visual processing and perception, making sense of what we see, and that's the focus of tonight. And the third part is using that vision to guide our actions. We need to be able to see that block in the road so we can stop on the brake pedal, right? We're going to start with the eye. I'm talking about vision, and I do have some eye models up here. Kind of a giant eye. Basically, light's going to enter into the front part and focus on the inside layer of the eye, which is called the retina. And so when that light focuses on the retina, we actually like for it to focus in a very specialized area where we have that 20/20 eyesight, which is called the fovea. So right back there in that area. And that is where our photoreceptors, or the cells that detect light, are the most densely packed. So if you think of pixels, the more pixels that are concentrated together, the more detail that we can see. And then our peripheral vision is more like our side vision, and we actually see things differently in those surrounding areas. Of course, we have different types of photoreceptors. We have rods, we have cones, and even in those cones, we have different pigments that are more sensitive to different wavelengths than other wavelengths. So there's lots of differences between those cells, but we know that those cells' job is to take that light information and send those signals to the brain. We have 5 million cones and 120 million rods. That's a lot of photoreceptors in that small little space, right? We're actually going to start processing that information even within the eye, and then we're going to send a big nerve cable back to the brain with 1 million nerve fibers. Because that eye is so specialized for clear vision, at the fovea, we actually have to be able to move our eyes around to aim them where we want to look. So we have lots of muscles to do that, to align those eyes perfectly, and I work a lot with patients, which this is a difficult area. But when I look at vision, I'm looking at different areas. One is how well we can pause, fixate, and take in information, how well our eyes can move and track, how clearly we can focus, and then how well our eyes can align to see single vision and to fuse that information. So our brain is really what adds that information from our right eye and left eye together. So let's try an experiment today. I want everyone to kind of look and tell me, do you see some colors? Nice little splotches of colors? Great. I want you to keep your eyes steady on that central black dot. It takes about 20 seconds. Anybody see something happening already? Anybody losing some of their side vision? Some of the colors are fading away? We're talking about sensory here. So when you put your shirt on in the morning, you can feel it. You start to notice it less and less throughout the day. You adapt your sensory. Same thing can happen visually. Now, to get those colors back, all you have to do is move your eyes. All right? Now, I was accused one time of having animated slides. So I actually made an art installation in the back during the break. If you want to try it on a piece of paper that's definitely not animated, you can. All right? Let's try another experiment. These are all part of what we call optical art, or op art, and some artists specialize on using some of these techniques. You're going to see some of those today. And so I want you to look around and scan this picture. Anybody see some movement? Raise your hand if you see movement. It's not going to be everybody. What happens if you look at one almond and keep your eyes nice and steady? Is it nice and steady and central? so when we move our eyes, our brain perceives that picture as moving, even though it's actually our eyes moving. And we see this in different directions and motions. What's happening here? Am I getting some spirals? Okay. Clinically, what I see is words moving on the page. And so I have a lot of patients, the reason they come to see me to get those eye muscles working better is because they can't coordinate that ability to pause and take in information and then move between words. And so it's confusing and it looks like the words are actually moving. All right, I already recruited a volunteer in the back. Mark, have you seen them? Who do you see in the back? Anybody know who that is?
From here, I'm actually getting a little bit of a double image.
All right, scoot back in the back.
From here, I'm seeing Albert Einstein.
Okay, so if we have that little picture in the back there, which I do have one on the wall, and you're far away and it's a little bit blurry. For those who can't see it, I actually have a lens to make it a little bit blurry. We can actually see a female feature. Does anyone see a female? Some people do. Who is it?
Marilyn Monroe.
It's Marilyn Monroe. As we get closer, or we see more of that fine detail, we're going to see Albert Einstein in the same picture. So we'll try that at the break. Who's angry and who's happy? So it might be different for the people in the front and the people in the back, right? And again, we have different parts of our vision being processed. Low spatial frequency, or that blurred edge, and fine detail. So yeah, if you have glasses, you can kind of look at a blurred image versus a clear image. So basically, once that information goes in the eyes, its job is to go back to the brain. It's actually going to go back to the very far back. We call that the visual cortex, or the occipital lobe. And all we know is I see that somewhere. That's all that part of the brain can tell us, is I see that somewhere. It means we detected the light was there, but until we get a little bit higher on in our processing, we need to figure out what is it and where is it. So that information goes from that back part, occipital lobe, up towards sensory motor, and down kind of towards our verbal section of memory. So I'm going to have you look at this picture. If you've seen it before and you know what it is, just go ahead and raise your hand. If you have no idea, I'm a terrible photographer. That's okay. Let's show you what it is. It's a cow. All right? So I know you can use your imagination, but again, dark could mean shadow, dark could mean edge, dark could mean just black area. But we're going to imagine that as an ear, some eyes, a nose, and the back. Can people see it now? So let me show you the exact same picture. Can you see the cow now? How many people? Can you raise your hand? Quite a few more people can see my cow. And we do that in art all the time, trying to find form, right? Clinically, first thing you do in an eye exam is read an eye chart. So yes, I want to make sure the light is clear back on your fovea, but I'm actually also testing your brain. Can you tell me what letter that is on the eye chart? Or in case of an infant, can you tell that these black and white stripes are there versus the same color of gray? What do you guys see? Some gray boxes. Anybody see a sphere popping out in the middle? Okay. So we measure depth perception. All right, that is, where is it? Do you see a circle popping out in number row 1? So we're going to talk a little bit today about looking at art, or into arts. And I got some demonstrations from our artists today, but I'm going to have Mike come over here real quick, because we've already tried this one. All right, Mike. Feel it yourself. Now, this is actually a therapy exercise that we use to train people how to aim where their eyes look. And so I have some extra mirrors in the back. You guys can all practice this as well. But my first thing I want you to do is look at the circle on the mirror and tell us what you see.
I see 3 eyeballs.
So poor Mike, 3 eyeballs. But that's okay because he's looking at the plane of the mirror. He's not looking into the mirror right now. He's looking at the mirror. So where his eyes aren't looking, he can see double or you can see something different. Now look into the mirror and actually focus on your eyes. Hopefully we fixed them from 3 to 2.
I now see 2 eyes, but see 2 circles on the surface of the mirror.
Perfect. So it almost looks like a raccoon, one ring around each eye, okay? So we can see completely different depending on where we're actually looking, all right? And our brain is going to be in control of that. All right, so lots of resources available to learn more about this part of vision, but I'm going to hand off to Lou.